Okay, several characteristics of dislocation are important, especially to the mechanical properties of metal. And this includes the strength field that exists around dislocation, which are influential in determining the mobility of the dislocation as well as their ability to multiply. So when metals are plastically deformed, some of the fraction of the deformation energy, approximately about 5%, is retained internally, and the remainder is dissipated as heat. So if we consider the edge dislocation represented in figure, some atomic lattice distortion exists around the dislocation line because of the presence of the extra half a plane of atom, and they are regions in which a compressive tensile and shear lattice strain are imposed on the neighboring atom. For example, the atoms immediately above, as we can see here, and adjacent to the dislocation line are squeezed together. And as a result, we can say that these atoms are experiencing a compressive strain relative to the atom's position in the perfect crystal and far removed from the dislocation, as we can see here in the figure. And directly below the half plane, the effect is just the opposite, where the lattice atoms sustain and impose a tensile strain, as we can see here in the figure. So we already know that around a dislocation, the atoms are displaced from their normal position. The atomic displacement are equivalent to that caused by elastic strain due to external stress. For example, the extra half plane of the edge dislocation puts the region above the slip plane into hydrostatic compression, while the region below the slip plane will experience tension. So this is how dislocation interact between them, as we can see here in the figure. I want you to consider the two edge dislocation that have the same sign and the identical slip plane. The compressive and tensile strain field for both lie on the same side of the slip plane, as we can see in this figure, and as a result, it will cause them to repel to each other. When two dislocation of opposite sign and having the same slip plane will be attracted to one another, and dislocation annihilation will occur when they meet. That is, the two half plane of atom will align and become a complete plane. Dislocation interaction are possible. Dislocation interaction are possible between the edge, screw, and or mixed dislocation, and for a variety of orientation. And this strain field and associated forces are important when we want to strengthen metals that we will discuss more in the chapter on a strengthening mechanism. So a different lattice will have a different bond and a different size, so the overall energy will be different. But for material, every kind of a dislocation has a fixed energy that we can associate with. Lattice energy is the energy required to break apart an ionic solid and convert its component atoms into a gaseous ion. So what I show you here in the figure is a process that we call as a polygonalization that can be defined as a movement of a dislocation. Here we can see that the original dislocation configuration, and once they are moved away from each other, the strain field will not acting severely on each other, and you might wonder why they are stacked up and arranged like this. This is because it will reduce the energy state of the system and become more stable, and the formation of these subgrain boundaries is a typical microstructural response to recovery process that we will discuss more about this later in the next chapter. So how can we define lattice strain? So we can define lattice strain as a slight displacement of atoms relative to their normal lattice position, normally imposed by a crystalline defect that may be due to dislocation, interstitial, or impurity atom. So in the last couple of lectures, we specifically talk about a point defect, which can be either vacancies or interstitial or substitutional. Also, at a given finite temperature, there is a certain concentration of a point defect that is thermodynamically stable. What that means is that there is a certain energy that is required to form this. So by introducing a point defect, you are increasing the entropy of the system. And we have to remember that this was zero-dimensional defect. What that means is that they are very localized. So if we talk about individual atoms, and therefore the strain or the formation of the crystal around them is relatively small. And in contrast, dislocation what we call as line defect that involve a large movement of atoms. We call it line defect due to the reason that they do appear as a line. So these are collective defect that do not depend only on a single atom. They depend on a number of atoms. And they propagate throughout the material along a different dislocation lines. So what you can see, for example, here in the figure, is the density of the dislocation can be really, really high. So remember that what is the definition of a dislocation? They are a line imperfection in otherwise a perfect crystal. And they are typically introduced into crystal during the solidification of the materials and also when the materials deform permanently. So a dislocation, we can define it as a line defect that exists in metals, and they are two types of dislocation. We have a edge and screw dislocation, and the symbol for dislocation is like this. So this is the symbol for dislocation. It is like a T upside down, and the dislocation density in anneal metals is normally equals to 10 to the power of 6 per centimeter squared. And here we can see the TEM or transmission electron microscopy image of an edge dislocation. We can see that the existence of a lattice mismatch and not that the extra half plane here at the upper side. And here we have amorphous versus the crystalline. And this figure show you the differences between the crystalline and amorphous state. And this would be an example or a transmission electron micrograph of a structure that is composed of silicon and silicon oxide. So in the case of silicon, you can see that the atom position is critically arranged. And if you look at the SiO2 here, we lose that periodicity. But if you look more closely into the image, you will also notice that this particular structure is not completely random. That if you look very locally, you will see some local arrangement of atoms that reflect the fact that these amorphous materials do have a short range order. So let us first define what is slip. We can define slip as a movement of a dislocation that causes the material to permanently plastically deform. And as the shear continues through the lattice, as we can see in the animation here, the plane is moved all the way to the lattice until emerges on the other side. And the planes on which slip occurs are what we call as a slip plane, and the direction of the shear are called slip direction. And the slip planes and the direction are the characteristic of the crystal structure of materials. So why do we call it slip or gelinciran in Malay? It is because the atoms slip past each other. They happen at a specific crystallographic plane in a specific crystallographic direction. Not just any atom can slide past to each other. Uh, they happen at the highest density plane in the highest linear density direction. For example, for FCC or fast center cubic, it is the most dense at this plane, and so slip will happen at this plane. And we can see that the plane will cut to all the atoms with the highest planar density plane. And here in the table, we can see the slip system for FCC, BCC, and HCP metals. So from the information here in the table, I want you to figure out why does HCC is brittle compared to FCC and BCC. As we already know, metals deform along the closest pack direction or the closest pack slip plane. And this is what we call as a slip system, where the bonds were breaking and reforming in order for dislocation to move. Since the atoms are closer together, so it is easy for bonds to break and reform in their closest pack direction.